can easily be detected by the AFSID as an audible sound as well as a variable LED bar display. The technicians maintain voice contact through the use of cell phones, and to make finding target cables easier and faster, the AFSID is connected to one of the cell phones. This allows the remote technician to hear the output of the instrument while various cables are tested. This amazing instrument makes possible for the first time the ability to identify specific fiber optic cables by simply tapping on them, and its wide dynamic range allows it to detect tapping sounds up to 100 kilometers away. The simple, quick, and non-invasive operation of the FiberPro AFSID ensures that poor cable management, faded or missing labels, or undocumented repairs will no longer pose a serious threat to your bottom line. This graphic shows how the AFSID system works. Light from a laser source operating at 1550 nanometers passes through an optical isolator, through an optical mixing and signal management module, to the optical ports on the rear of the instrument. Using optical jumpers, these ports are terminated to a pair of spare fibers in the cable to be located, and a loopback jumper or connector is applied to the fibers at the remote end of the cable span under test. The optical mixing module ensures that light from the laser travels in both directions around the fiber loop, forming an interferometer. Because laser energy is coherent, splitting the laser light into a pair of beams and allowing them to interact over a long fiber span produces a pattern of interference in the fibers. If the light were visible, this interference pattern would show up as a series of brighter and darker regions along the fiber span. The interference pattern also returns to the optical module, where it is monitored by a detector system. However, an optical isolator prevents returning light from entering the laser's optical cavity, which would cause system instability. Under steady-state conditions, the interference pattern would not change along the fibers, and the detector would see the same intensity of light over time. However, if the cable is bent, moved, or even tapped with a solid object, microbending slightly changes the optical path length the laser beams are traveling in. This moves the position of the interference pattern in the fibers, so the detector will now see a difference in light intensity that varies with the strength of mechanical perturbation of the cable. In this way, the entire cable span acts as one giant microphone that is extremely sensitive. As an example of the sensitivity of the AFSID system, if a 20 kilometer reel of bare fiber is terminated to the instrument, the reel